So we are going to the next session, session 5, which is a short session with just 2 papers. This session is on sensing and learning. I'm going to have the first speaker come up. His name is Wenjun Jiang, and he's a 5th-year PhD student from the University of Buffalo. He is working with Professor Lu Su, and his interests are in mobile computing, wireless sensing primarily. And he's looking for a summer internship. So if somebody is interested, please do come and talk to him. And here he's going to talk about device-free human activity recognition.
Thanks for the introductions. Today, I'm going to present our paper towards environment-independent device-free human activity recognition. This is a joint work with my collaborators from SUNY Buffalo, UIUC, and Beijing University of Technology. What is device-free human activity recognition? It refers to techniques that utilize the information in the wireless signals to recognize the activities without the monitored subject to carry any dedicated device. It has a wide range of real-world applications, such as the smart home, fitness tracking, and healthcare. Why can we recognize activities from wireless signals? You see, when the man is between the transmitter and the receivers, his activities will incur changes to the transmission pattern of the wireless signals. Based on these principles, various wireless approaches have been developed, but there is a common challenge that has not yet been solved. For this example, we can see the wireless signals not only influenced by the activities, but also by other objects such as the bed, the chair, the wardrobe, and the body shape of the human. So we can see that the wireless signals contain both environment-specific and subject-specific information. As a result, the model we learn from one environment for one subject typically does not work well when apply it to recognize activities for another subject in another environment. To solve these problems, we propose an environment-independent recognition models called EI. In these models, we make use of both labeled data and unlabeled data from different rooms. Then our goal is to extract common features that is used in different subjects and the different environments to predict the labels of that unlabeled data. Let's take an overview of our systems. First, the data collection process. We assume that the activities are monitored from different rooms with a specific wireless device. We collect data from all these rooms. Then, for some rooms, we can obtain the labeled data, and for the others, there are no label information. Next, we will normalize the input data and transform it into a form suitable for analysis, and then split into short segments as the input to our deep learning-based models. We use deep learning techniques because it is effective to extract discriminative representations from complex data. Our deep learning models is composed of a convolutional neural network and an adversarial network. And last, it will output the activity data estimation. Next, we will elaborate the structures of our proposed model. Our proposed model mainly contains 4 parts: the feature extractor, the activity recognizer, the domain discriminator, and the 3 constraints. First of all, the feature extractors is to extract features from input data. The activity recognizers will give label estimations for both labeled data and unlabeled data. For labeled data, since we have ground truth, so we can maximize the label classification accuracies. But for unlabeled data, we do not have ground truth. So our goal is to increase the confidence of the estimations, because increasing confidence, we can at least draw the boundary away from unlabeled data. And the third part is the domain discriminators. Here we define the domain as the pair of room and the subject. The goal of the domain discriminator is similar to the activity recognizer on labeled data, except that it is not to estimate the activity label, but to estimate the domain where the input data comes from. To solve some practical issues in the proposed models, we propose 3 constraints. The first is the confidence control. We use confidence control to penalize the estimation that has overconfident, so that we can keep a proper ratio of all the label estimations in order to avoid overfittings. The smoothing constraint is also intuitive, as encourages the points around the input data to have the similar activity estimation, so that there will be no abrupt estimations. The model will be more reliable. The last one is the balancing constraint. The motivation is that we want the training process will not form large clusters of unlabeled data, because it will distort the learning of representations. Recall that our goal is to remove domain-specific information. So our feature extractors need to extract features that cheat the domain discriminators but boost the activity recognizer. We can use this loss, LA plus alpha LU minus beta LD. Note here, we use the negative LD, which means the goal of the feature extractors contradicts to the goal of domain discriminators. The problem comes, how can we train these models? In order to show the training process, we first visualize the latent representations output by the feature extractors. Actually, the data has the dimensions higher than 2, but we project into 2 dimensions for visualization. The points with the color blue and red are activities from 2 different domains. We can see that they are separate because the activities contains domain-specific information. Next, we freeze all the parts except the domain discriminators. Here, the freeze means that we keep the parameters in this part unchangeable during the training process. After we update the parameters, the effect of the domain discriminators is to learn a boundary between these 2 domains to maximize the domain classification. Next, we recover all that parts and freeze the domain discriminators. Since the goal of this part is contradicts to the domain discriminators, the effect will be that they will move the points towards the boundaries so that they are harder to be distinguished. We continue to do these 2 parts. After we update the domain discriminator again, a new boundary will be learned based on the current data representations. After we update the other parts, the points will be drawn even more closer to the boundaries until finally they are harder to be distinguished. We evaluated our methods on 4 test beds: the Wi-Fi, the ultrasound, 6 GHz millimeter wave, and the visible light. The first task we did is the activity recognitions, which is conducted on 3 mobile devices. We estimate 6 activities. We employ totally 12 subjects in 6 rooms in 2 different buildings. We emphasize that there are no common rooms for the labeled and unlabeled domains, which means that for the room where we need to estimate activities, there will be no label information. And the Wi-Fi signals as collected in this environment The transmitter as the Wi-Fi access point, the receiver as a device equipped with 5300 network interface card. We collect the CSI at 200 Hertz. To compare with our method, we utilize 3 baselines. The first is the random forest, and the rest 2 are true state-of-the-art domain adaptation method. The difference between the method and ours is that the random forest do not utilize the unlabeled data. The second one does not consider the confidence of the unlabeled data, and the third one do not control the confidence and the training process. The result is shown here. We gradually increase the number of labeled domains from 2 to 22 and show the accuracy of the label predictions. We can see here, when there are only 2 labeled domains, all the methods have a low accuracy because the label information is too little to learn a good classifier. When the number of for the random forest, even when the number of labeled domains increases, the performance does not increase because the wireless signals are sensitive to the environment, and the model that is trained on the labeled domains cannot work well for to predict the labels on different rooms. And all the other methods can get improvement when we add the number of source label domains. But our methods improves much more than the others because it utilizes unlabeled data more effectively. We also show the learned representation from our models. Here we assume there are 2 activities collected from 2 different rooms. We use different colors to represent 2 different activities and 2 different markers to represent 2 different rooms. We highlight 2 points here. They are the same activities but collected from different rooms. The original data of these 2 points are illustrated here. It is not hard to see that although the original signals are quite different, after using our models, the data are mapped to a hidden representation that make these 2 points close to each other, which demonstrates that our methods can indeed remove domain-specific information. The ultrasound experiments are using the iPad mini as the transmitter and the smartphone as the receiver. We collect the raw ultrasound signals at 44.1 kilohertz. The results shows the similar pattern as the Wi-Fi signals, except that even as long as we have only a few labeled domains, the methods can learn a relatively good classifier. The experiments for the minute wave uses the X60 for both the transmitter and the receiver, and we collect the channel impulse response at 25 Hertz. Since the millimeter wave usually are made directional, so the improvement of the environment-independent models is not as much as those for the Wi-Fi and ultrasound. The second task we use is the gesture recognition on visible light. We use it to recognize 4 gestures. We totally employ 6 subjects and conduct experiments under 3 different lighting conditions. Similarly, we require that there are no common subjects in both labeled and unlabeled domains. We use the transmitter as the portable USB lamp, and the receiver are the CDS cells as the photoresistor, and the Arduino Uno as the controllers. The experiments data we collect as the resist value at 15 Hertz. The result shows that our model can also learn the subject-independent features. To conclude, we propose an effective and general environment-independent framework to recognize device-free human activities. Framework is composed of 4 parts: the feature extractors, the activity recognizer, the domain discriminator, and the 3 constraints. Our framework is effective on 4 testbeds, including the Wi-Fi, ultrasound, 60 GHz millimeter wave, and the visible light. Thank you.
Our second speaker for the session, Ji Zhang. So she's a PhD student at Northwest University in Xi'an, China, and her interests are in human recognition and human identification and gesture recognition, and also in wireless security. She's here to talk about large-scale Wi-Fi sensing.
And thanks for the introduction. Good morning, everyone. I'm Ji Zhang, come from Northwest University, China, and today I will present a paper, cross-science towards cross-science and large-scale Wi-Fi sensing. This work is done by these universities and these guys. Wi-Fi is a powerful sensing medium by measuring how the various channel metrics are affected by humans and their activities, and then correlating the measurements to pre-collected fingerprint, human rich information such as gait patterns and gestures can be identified. Then it because the measurements collected for different persons or different gestures are very different. So it can be seen as a fingerprint for the humans or for the gestures. As a Wi-Fi sensing system needs as few as 2 common Wi-Fi devices, not requiring instrumenting the users or less privacy than other infrastructure-based solutions, such as video monitoring. Wi-Fi sensing has huge potential, such as in smart house, a user can perform a gesture to control the device, such as turn on the light or turn off the video. For virtual reality, the user can perform the gesture to start a game, or even the system can also monitor the user's voice for the user's health check. But there are 2 limitations. Currently, first, current methods requires collecting training environment for each target subject or each target activity from every single site. Thus, collecting training environment will be a labor-intensive and time-consuming process. Then it because the measurement collected for the same person or the same gesture are very different across sites. Thus, if we want to identify 100 users in a company in all the testing series, we must ask the user to work several times in all the testing series. So, it may annoy the participants. Secondly, many sensing solutions only support a handful of activities. As shown in the slides, the performance will decrease quickly when the number of the targets is larger than 100, and we can see the accuracy can only achieve by 30%. So, in this paper, our goal is to scale up Wi-Fi sensing to new environment and a larger problem size. Scaling up Wi-Fi sensing to a new environment means that the training measurement can be collected in one site but can be used across sites. Scaling up Wi-Fi sensing to a larger problem size means that the system can also have the good performance for larger problem size and consistent performance no matter the problem size. So, this slide gives a high-level idea of cross-site sensing. So, if we can learn how does the environment affect the Wi-Fi signal, and we can easily transform the training environment for any on-site users or gestures in a new environment. I show in the slides, if we can train a roaming model for two environments, we can easily use the transformation function to transform the input signal matrix of site A to the translated signal matrix for site B. These slides give us the high-level idea of our larger problem sensing solution. So, current methods have low accuracy because they use one sensing model for all the training measurements. But if we can dynamically choose which sensing model should be used for the input Wi-Fi signal, the accuracy will be greatly improved. I show in the slides, if we can use an expert selector to choose a proper model for the input Wi-Fi signal, and the model is specialized for the application theory and the input model, the testing case will be correctly testified. So, how does the system work? These slides give us a general view of how cross-site work. To enable cross-site sensing, we employ machine learning to learn a roaming model to roam the Wi-Fi fingerprints from one environment to the new environment. And the roaming model is trained offline on a set of examples collected from the deployment site and the collection site. And then the roaming model is used to transform the fingerprint features for any on-site users or gestures. To enable Wi-Fi sensing to a larger problem size, we employ machine learning classifier to choose a proper model for the input Wi-Fi signal. Depending on the characteristics of the input Wi-Fi signal, different models will be dynamically selected. So, before building the model, what can we do? The input of the model is not the raw signal, and we extract features to capture the most important right channel metrics. So, we extract four kinds of features. After pre-processing the data, we apply a learning algorithm over the collected data collected from deployment site and the collection site to construct the roaming model. And the roaming model is trained offline on a set of examples collected from deployment site and the collection site. And besides, the input of the model is the feature values of the data collected from the collection site and the deployment site, and we will the features will be put into the learning algorithm to construct the roaming model. So, after translating the Wi-Fi fingerprint to each deployment site, we need to find ways to effectively use the translated fingerprint. An expert selector decides which model should be used for the input Wi-Fi signal. And our approach allows new models and new features to be added easily. So our expert model are trained on a set of machine learning classifier, and each modeling technique can be used in combination with one of the feature sites to determine which feature model combination should be used should be included in our expert model sites. We perform cross-validation on fingerprint data sites, and we will keep the combination if the combination can give the highest accuracy, or it can correctly classify the testing cases where other combinations fall. And our expert models are trained offline. After building the expert models, we will have a mechanism to decide which of the model should be used for the input Wi-Fi signal. And our expert selector is a KNN class affair, where K is set to be 3, and the distance is measured by applying the dynamic warming algorithm. So, after using the roaming model and the expert selector, how well does the system work? We compare our approach against four state-of-art CISF sensing, and this includes 2 current methods for gate identification and 2 current methods for gesture recognition. And prior methods can only target a handful of users or activities, such as for gate identification, the current methods can only solve tens of participants, while our system can solve hundreds of participants. For gesture recognition, prior methods can only target handful of gestures. We thoroughly evaluate our approach in 3 indoor environments of different sizes, and they are separately hall, corridor, and office, corresponding to low, medium, and high multipass. And we recruit 100 users to participate in our experiment, and we consider 40 gestures presented in prior work as our final gestures. And the experiment lasted over 3 months. These slides give us the results, and it shows how the classification accuracy changes when the problem size increases for CISF sensing. The first 2 bars are current methods, and the last are our approach. And the training environment and the testing environment are collected from the same collection site. So, I show in the slides, current methods deliver worse performance as the problem size increases. And the accuracy can drop by 20% for gate identification, and when the user size is larger than 50, and when the number of the gestures is larger than 5, the accuracy can drop by 20%. But when targeting 100 users and 40 gestures, the accuracy will be dropped by more than half. By contrast, our approach improves the precision greatly. I show in the slides, our approach not only delivers the best accuracy in all the testing scenarios, but also performs consistent performance across the scenarios. These slides, we evaluate how our roaming model enhances existing Wi-Fi sensing methods when the fingerprints are not collected in the deployment site. We test the current method on 6 targets at a time, and these slides compare the accuracy with and without roaming. Without fingerprint roaming, the training environment are collected in the collection site, and the testing environment testing data are collected from the deployment site. So, I show in the slides, without fingerprint roaming, all approaches can achieve by only 20%. But our approach gives a clear boost to Wi-Fi sensing and improves the accuracy by over 4 times. So the results show that our roaming model can help the current method to maintain the level of the accuracy if the fingerprint is not collected in the deployment site. In this experiment, we evaluate the overall performance combined fingerprint roaming and mixture of experts for 100 users and 40 gestures. I show in the slides, existing approaches gives disappointing results. That is because the measurement collected for the same person or the same gesture are very different across signs. So if we try to use the training environment collected from the collection site as a training environment, as a training data for the deployment site, the accuracy will be very low. But our approach, these lines will give us a conclusion. So the problem is that Wi-Fi sensing is great, but limited to small-scale deployment. We employ machine learning to solve those two problems, and the experimental results show that we improve we have 4 times improvement on the accuracy, and we work effectively for the problem sizes. That's our work. Thanks for your attention.